Okay, today we're going to talk about real numbers. Real numbers, which you need to know some of these definitions for ACT, SAT. They're going to use terms like that. It's not so hard. Any number on a number line. So really just about any number you've ever seen. Pi, even pi is irrational 3.14. Could you put on a number line? Sure. What's not a real number? So what's not a real number would be a number like square root of -4. Try typing that in your calculator. You're going to find that it says not a real result. Square root of negative will not give you a real number. It's not a number you can put on a number line. Later on in class, we'll learn that a problem like that is equal to, say, 2i. It has an imaginary number there. We'll learn about that later in the year. I'm going to save that, but just know that if you have a square root of a negative number, if you have a negative there, you don't have a real number. Pretty much everything else you've seen in math class is a real number. Rational numbers. So now this one is one you should be familiar with, although I find that students many times are not familiar with this one. There are two definitions, two ways of defining this. The first has to do with decimals, and you might remember this. So if you're talking about decimals, then you are saying with rational numbers that it is, let's see, so repeating. Rational numbers are repeating or terminating decimals. So terminating meaning it stops, like 5.2. It would be a terminating decimal. Repeating, something like 1/3. Oh, sorry, something like 0.3. Repeating. That would be like a repeating decimal. So you can define it as terms of a decimal. So that's one way of defining it. Another thing is define it really as a fraction. And so really any fraction of integers forms a rational number. So like the number 5 is rational because 5 divided by 1 is a fraction of integers. 0.3 repeating is 1/3. That's a fraction of integers, so that's also rational. 5.2, we can figure out what that is, how many seconds that is. That's like, would that be 52 tenths? Would be one way of saying that. So that's definitely rational. It's a ratio of integers. It's a fraction. In fact, that's kind of code. If you want to kind of think about that, that's code for when you see the word rational, I want you to think fraction. Those two things are connected. Oftentimes in math we say, oh, we're studying rational numbers. Oh, well, we're really studying fractions. So that's one way of kind of thinking through that. Finally, we get to irrational numbers. And some of you may know some of the most famous ones, like pi. It's very famous. And the decimal, if you're talking about the decimal, let's think about pi. It's non-repeating. It's a way of saying it goes on forever. That's how we say that mathematically. And non-terminating goes on forever. Sorry, I got that wrong. Terminating. Non-terminating goes on forever. And non-repeating, meaning it never repeats itself. So 3.1415 and so forth. So it never, no matter how many digits you memorize, it doesn't ever repeat. They've gone millions of digits, and it doesn't ever stop. So it doesn't ever terminate. More common ones besides that one would be something like this: square root of 2, square root of 3, square root of any non-perfect square. The square root of 4 is not irrational. That would be rational because that's equal to 2. And 2 can be written as a fraction, 2/1. So that would be an example of a rational number. So any non-perfect square you try to take square root of that's not negative, that would be irrational. Okay, so knowing that, let's figure out some of these problems here. And we're going to label some of these things. So we're going to call all these numbers here on the left are real numbers. We don't know much about these imaginary numbers right now, but I'm just going to call this side imaginary. There are two types of real numbers. So there are rational and irrational. And a type of rational would be an integer. You're very familiar with those probably. Integers can be, don't have a decimal to them, like 1, 2, 3, 4. They can also be negative, -1, -2, -3, or they can be 0. Whole numbers are very similar. You've heard of these before. They start counting at 0 and go up, 0, 1, 2, 3, 4, 5. And then these are called natural or counting numbers. So natural numbers or counting numbers, you start counting at 1, so they go 1, 2, 3. Natural numbers do not include 0, whole numbers do. So let's think about putting some of these things in the proper place. Negative square root of 7. Well, square root of 7 is a non-perfect square. Not negative there, so that would be, it's not negative underneath the radical, so that would go there. 2 pi plus 5, again, irrational because pi is irrational. 2.35 is repeating, so this must be rational. Square root of 5, square root of negative 5, I should say, is imaginary. You can't take the square root of negative. 5 plus 2i. It's actually in this, it's kind of a combination of real, that's a real part, that's the imaginary part. So this is called a complex number. I didn't mention that one, but that's the bigger category here. By the way, I need to mention this. So some of these numbers, like for example 0. 0 is a whole number, but it's not just a whole number. The way this Venn diagram works, 0 is also an integer, is also rational, it's also real. Same thing for this. Rational, 2.35 with 3.5 repeating, is rational and real. This number is irrational and real. 4.78 would be terminating. Square root of 121, if you simplify it, is 11, which is natural number, which is also whole, which is also integer, which is also rational, which is also real. And then this is one of the more famous ones we'll learn about later in the year. It's an irrational number, kind of like pi. It's called Euler's number, E. So that's kind of a neat one we'll learn more about later. Express as a fraction, so can you actually express that as a fraction? So hopefully you can. One way of doing that is to say, well, that equals to x, right? So if I do, say, 10x, 10x would be 8.88 repeating, or 0.8 repeating. So if I subtract that, for example, x minus 10x is, that would be -8 equals -9x, because you see the 0.8 repeating, 0.8 repeating cancels out. You're subtracting that. And so you get, if you divide by -9, you get 8/9 equals x. Kind of a neat way of solving that problem. So we can figure out, some of you might have known that, by the way. It's kind of a shortcut you learned in elementary school. 0.8 repeating is 8/9. 0.3 repeating is 3/9, or 1/3. What if you had 0.77 repeating? That would be 77/99. That's another way of solving that problem. Let's try this one now. So just the 7's repeating. So let's try that again. Let's call it x. And let's say 10x is equal to, I don't know if this will work. Let's see. So it'll be 3.77 with the 7 repeating. So if I subtract, I get that is, well, let's just make this easier. Let's move this down here, right? I keep making this hard on myself. Rather than rewrite that, it would be easier. And usually it's better to take the easier way out. Let's say the x is here, and this is 0.37 repeating. So let's subtract this guy from that. So this, now we get a positive number. That is easier. And we subtract here, the 7's go away. They're in the same spot, the 100th spot. So it'd be 3.7 minus 0.3 is 3.4. So we have 3.4 divided by 9 x, which is like 34 divided by 90, which could be simplified a little bit, but that's basically your answer. What could that be? Like 17 over 45. And I think that's probably simplified. Now this is just a little tweak on this, just a little bit harder. I like to challenge you sometimes. It says if I just multiply by 10 here, like if I say x equals 0.83 repeating, multiply by 10 would be 8.38. 38 doesn't subtract nicely, so this is a little trick. Multiply by 100, moves it over 2 decimal places, 83.83. Repeating, these cancel. When you subtract, you get 99x equals 83. So x equals 83 divided by 99. You need to do this, be able to solve this by hand for the quiz and the test here. Just a few more things here. Open and close, unbounded. So this is open is like this. Closed is like this guy. That means it includes that point. This does not include -2. Bounded and unbounded. To get confused. This is unbounded. Because why? It keeps on going, at least in one direction. Because in this direction also. This is unbounded. It keeps on going forever. This one is bounded. Because why? It has a starting point and an ending point. It does not go on forever in either direction. One way, so if you say something in words, like b is at most 5, so if you have 5 on there, at most means equal to or less than, in that case, at most. So that graph would look like that. C is less than 4, but at least 1. So if I have something like that, at least 1 would look like that. Let's see, that would be at least 1, includes 1. But less than 4 would be something like this. So this is 4, an open circle at 4, because it's less than, not equal to 4. This is an AND statement, so we're saying both those are true. This is one way of solving this problem. So I might think about it this way. If we have our, this is -2, and this is 5. So if I kind of did my thoughts up above, if I do this guy up above, that's going to look kind of like this, greater than 5. If I do this guy up above, that's going to look kind of like this. Looks like that. Now, combining both of those together, oh wait, sorry. I think I did that wrong, didn't I? Wow, that was really bad. Let's combine both of those. Let's redo those. So the arrow here, x is less than 5, so that graph would look like this. And x is greater than or equal to -2, that graph looks like this. So the AND statements mean both are true. Where are those things overlap? Where are both of those things true? Well, between. So your actual graph is not either one of those. I just showed my work up there. What is the graph of all of that? Simplified would be just the overlap. Starts at -2, closed circle, and over to 5, open circle. That would be the final answer here. Not all this work up here. We don't want to see those each individually. We want to see the solution there. Similar for this. If I were to bring this down here, -2, 5. Okay, if I do this one, so now I'm saying x is less than 5, that looks like this. Or x is greater than or equal to -2, looks like this. So now when it says or, I'm not looking for both of them. I'm looking for either one. This or this, the blue or the green. So what number is not covered by either the blue or the green graph? Well, it looks like every number on the number line is covered in one direction or another. So the actual answer on this one is kind of sneaky. It's going to look like this. It's going to be the whole number line. Now this is a little bit of a sneaky problem. Oftentimes these OR graphs more typically will look kind of like this, where you have a starting point and then you go in each direction. That's the more typical type of ore graph. But I wanted to show you a hard one like you might see in homework.